Hey, Mark Dingman here from Dolphin Structural Solutions. I've not done one of these YouTube videos for a while. I'm just finishing up a very big project that diverted a lot of my energy, but I'm back now to do stuff like this. And ironically, one of the first things I see this morning on the internet was a video that Lucid put out about gravity crash testing. There's some interesting things in there, so I figured I'd do an observation video. And Daphnis.co, that's my gateway for automotive structural consulting. Interested to know more about my background, head over to Daphnis.co. We're going to run this video the same way we've done some of the previous ones that I've done, because Lucid did not release this video as a YouTube Creative Commons license, which means that I cannot take snippets of their video and put it into mine. So the way we're going to run this is you're going to need to load up their video, and you're going to find that either by searching in YouTube for crash testing Lucid Gravity, or go to Lucid's YouTube channel, which is Lucid Motors, and look for this video. You're going to load that up into a different browser. Keep me going here. I'm going to talk about different time steps in the Lucid video that we'll stop at and talk about what we see in that particular frame of their video. Before we do that, though, some background on the Lucid structure. This is an image here of a Lucid Air. It's something that I can use and talk around, but the gravity is very similar. From a body perspective, it's an aluminum body frame integral execution. It has a front corner casting, which comprises the torque box and the front shock cap. It has a hole or an arch in the mid rail to allow for the front half shaft to pass through it. And this is an arch in the body. It's mended, if you will, by the cradle as it bolts up to the body. This gray T-looking thing is a PowerPoint engineered representation of the cradle structure and how the cradle fixes this hole, if you will, once it's bolted to the car. And this vehicle has rather large extruded front compartment mid-rails. My recollection is that those are multi-hollow pieces, and you can check me on that. You may notice that this vehicle and this body execution strategy, design strategy, is very similar to some of the elements that you see in a Tesla Model S or X, and that is because there is some personnel lineage between Lucid and Tesla during that time of the S and X. The cradle of Lucid, and I've got a picture of a Lucid Air cradle. This is from their media site, so I can use this. So it's a little bit different. I marked it up to represent the gravity. So the gravity cradle is primarily a cast front cradle, aluminum cast, and we see that represented by let's call it the darker green color. It does incorporate two aluminum extrusions, one going forward to what we would call a lower fascia support beam or a lower impact beam. And the second one here called out as B. This is going off, and it looks like its only purpose in life is to interface to the IIHS-SOF barrier. It also has a shear panel, a sheet shear panel glued and screwed to the bottom of the cradle, and that's represented here by the lighter green. I'm going to call this a non-traditional 4-point cradle with no rear attachment, in that we would look at this and say it has a front attachment. We would normally call this a mid-mount attachment. The rear attachment tends to be out at the rear in the body 1-bar inner torque inboard torque box kind of area of the body. But what we see here with the Lucid cradle is that it's somewhat disconnected from the underbody of the car in the 1-bar vicinity. The cradle also provides interface for a forward-facing lower control arm suspension layout. We see that in orange here. We see a handling link here, and the ride link going forward to the ride bushing, forward facing because it travels forward of the axle rather than rear in a rear facing lower control arm configuration. We'll see why that's significant. So differences between the gravity and the air. Mentioned that the gravity front cross member is integrated into the casting. The air, this is a separate extrusion. And at least in the first model year of the air, it did not have this horn extrusion labeled as B. So the first load case that they go into detail on is the full frontal. And that goes between 57 seconds and 1 minute and 17. And I'm looking at a picture here, a snapshot at 1 minute and 2 seconds. It's from the side view animation of this subsystem test. And what we see in this frame is, number one, they are releasing the front cradle front attachment. If you've seen at least the Lucid Air front cradle in person, this attachment has a keyhole slot. It looks like something that is designed to release, and we see here in the animation that it certainly does release. The second thing we see is that the front cradle undergoes a V-bend shape in the side rail between the mid-mount and the front mount. And that's engineered by tuning the fracture behavior of the casting just forward of the mid-mount. I think it's pretty impressive, interesting that they're confident on the body corner casting strength, because it's not part of the parts being tested in this subsystem physical test. It's actually represented in the fixture. So they're considering that body corner casting that has the arch in it is not going to yield, not going to crack. It's also interesting, right? Notable. They include the lower control arm they include the lower control arm front member in this test. It makes sense if you understand the load path of what's going on there. Its attachment into the cradle is highly loaded. It makes sense that it's there. I think to the casual observer, it's kind of funny of, well, why did they include that in there? It's just kind of hanging out in space, but logical for sure. The top view of this test can be seen at 57 seconds, same test. I think what's most interesting, at least first glance at this image, is the extent at which the engineered cracking occurs in the cradle side member in the casting. Sometimes it can be challenging to engineer repeatable cracking in a casting, but it does look like they've done that, and they did use the word robustness in their narration of this video, so sounds like they did a good job there. The second load case that the video dives into fairly deeply is the IIHS-SOF, the small overlap frontal barrier, and that occurs between 118 and nearly the end of the video. Whenever I think about SOF or talk about SOF, I like to ground myself in the two fundamental behaviors required to execute a glance crash mode shape, and they are building lateral velocity in the vehicle and expelling the wheel corner. With regards to building lateral velocity, looking at the video here, it's evident that the horn engagement to the barrier is working well, and it's driving load into the plan view, top view shear stiffness of the front compartment and the cradle. The vehicle is getting off the barrier very well. Expelling the wheel corner, I'll say that I've been waiting to see this for a while, because this car has a forward-facing lower control arm front suspension configuration, and executing a glancing crash mode in SOF is very rare when you have this configuration of your suspension. Lucid mentions that it took a lot of time to do this, but they accomplished this through tuning and engineering the strength of the suspension knuckle and the linkages that hold the wheel corner onto the car. Some of the detailed notes down here between 140 and 142, and again at 147 to 149. My picture's at 147, my snapshot. And we can see that the front cross member of the cradle is fractured. Just an observation, it was an extrusion on the air. they incorporated it into the casting, and the gravity likely to save some money. It looks like they still performed as well as they wanted to with that front cross member cracking. And then at 146, this is a larger view of the front corner of the cradle, and it's kind of hard to orientate yourself here a little bit because the part's so mangled. But the front of the cradle is facing forward of us, and the narrator's thumb is basically at the root of the horn. The horn is hard to see here because it is nearly destroyed. It's taken a lot of load, and certainly a lot of plastic deformation there. At 150, we can see elements of their CE model. We can see elements of a good glance crash mode execution. The first one is the folding of the front impact beam extension. We can see also in this video here that the wheel behavior certainly demonstrates the expected kinematics of a forward-facing lower control arm. Not ideal for this, but they certainly expelled the wheel through their separation strategy and execution. And here we see the execution of their separation strategy with the suspension links separating at the knuckle joints. And lastly, we can see in the animation, we can get an appreciation anyway for the wheel tire stacking up to the front body hinge pillar. If you've seen this area of the car on the air, it would certainly explain the magnitude of reinforcement that they have in this area, to simply to deal with the impact of the wheel corner onto this area. And then lastly, this happens pretty quickly at 39 seconds. Give you a second to find it, but I will say, this is a post-test picture of the SOF vehicle on a hoist. There's not a tremendous amount that you can pull from this that we haven't already talked about. My image is kind of blurry, but I think it just gives an impression from the full vehicle perspective and maybe a different camera angle. I think you can see some of the front body hinge pillar and front side door damage that occurs in the test because of the wheel and the behavior of the wheel and how it expels. But yeah, that's there, and maybe you can see some more. And that's it, a quick one on the Lucid Gravity. If you like this stuff, if you like this video, please hit like. If you like the content generally of the channel, please hit subscribe. It motivates me to make more of these. So thanks for that, and have a good day.